curves. Okay, so we were in the situation where stable curves of genus G with n-marked points even exist, and we fix one such, a curve x with n-marked points, p1 through pn, in fact, which is smooth, n-marked of genus G. And this is all over a non-Archimedean valued field. Which I will just assume is complete and algebraically closed. So it's complete with respect to its non-Archimedean norm, and it's algebraically closed. And again, this is not too much of a big deal. One can always make a make a big field extension to ensure that this is the case. And we noted that by the celebrated stable reduction theorem, this curve has a stable model, curly x, p1 bar through pn bar. So here x is over R, the valuation ring associated to K. And this is a family, a flat proper family over R whose special fiber, whose generic fiber is isomorphic to x, and whose special fiber is some stable curve, again with n-marked points, which are somehow the horizontal closures of the points p1 through pn on the generic fiber. So here I was calling this curly x sub little k, the special fiber of curly x. And this is precisely a stable curve. Again, at the same genus by flatness, say, and with the same number of marked points. Okay, then recall that the tropicalization is some combinatorics that's associated to the special fiber of a stable model. Namely, it's the dual graph of this special fiber, equipped with some edge lengths that record something to do with the local equations of the nodes on the special fiber. So I'll just write that we got, let's see. So from this data, we get the data of a graph. This is the dual graph of the special fiber with vertices corresponding to components and edges corresponding to nodes. And we have a marking function. This is just some sort of extra data decorating the graph. A marking function that remembers where the marked points go, and a weight function that remembers the geometric genera of the components. Okay, so this is the vertex marked, the vertex weighted n marked dual graph of the special fiber. And to make this a tropical curve, we equip the edges with the following length function. So we note that a node, say Q in the special fiber, has local equation viewed now as a point not just in the special fiber, but an actual closed point in the surface, curly x over spec R. It has local equation of the form xy minus alpha for some alpha in the valuation ring, in fact, with positive valuation. And this alpha is not uniquely determined, but its valuation is. And we let the length of the edge in the dual graph associated to that node, Q, we let that be, the valuation of alpha, this positive number. And so this is the tropicalization. This is the abstract tropical curve, in contrast to the plane tropical curves we encountered in the first lecture, associated to your curve x with the marked points. Is it okay? That's where we got yesterday. Okay, let me remark just briefly that I can, without much effort, extend this definition to the case of stable n-marked curves. Yeah. So let me just say it's easy to extend this tropicalization procedure to stable n-marked curves of genus G, but in the sense that the stable reduction theorem still holds. So you start with the stable curve on the general fiber. You can still fill in the special fiber with the stable curve now over the algebraically closed residue field. And so what is the tropical curve that you get out? So again, let me again let X pi bar be a stable model. So again, we consider the dual graph, the vertex-weighted marked dual graph of the special fiber. Okay, so I really should write the marked points on the special fiber, but I'm omitting that from the notation. I hope that's okay. And now in this case, the edges of the tropical curve, okay, let me put it this way. So consider a node on the special fiber, now of this stable model where the generic fiber might no longer be smooth. Well, that node may have local equation of the form xy minus alpha, where alpha is some number, some element of R with positive valuation. Or alpha could be 0, right? So, so then Q, a node in xk, may indeed have local equation of the form x times y equals 0. Oh, sorry, is it clear what I'm saying? So I'm just saying that there's a very, we've already developed this theory and it's very easy to extend it to the case of stable curves. And the only fix we have to make is that now nodes in this special fiber may have they may actually correspond to a local equation x times y equals 0, which indicates that when passing to the general fiber, the node simply persists. So the node here may well come from a node on the general fiber. And in that case, the parameter alpha we'd like to take is 0, and thus we'd like to simply slightly enlarge our definition of a tropical curve to allow positive infinity as a length, a permitted length on the edge. In other words, the valuation of 0. So thus we may associate an extended tropical curve to x by taking the length of the edge e sub q to be plus infinity. So what is an extended tropical curve? It's the same thing, except here I allow, so we simply permit ourselves to have both positive numbers and infinite edge lengths. So that's just a small edit to the previous definition, which just comes from the fact that if you have nodes on the general fiber, they can, they will persist as nodes in the special fiber, and those edge lengths are deemed to be positive infinity. Is it okay? Okay. So if you'll permit me just to repeat some more, let me just do over the example I gave on the first day, now equipped with all of these definitions. So we'll do over the example of a conic with 4 points on it. So a plane conic with the equation x times y equals t to the L. L is like some, say, positive integer. That's totally fine. And this is an equation defining a conic in the projective plane over some some valued field with a local parameter t on the base. So maybe I'll take k, e.g., to be the completion of the Puiseux series. Whatever. You can just think about it as over the field of Laurent series, which is very familiar. And let's take, to make this stable, right? So this is, of course, a rational curve in the plane. So let me make this stable by adjoining, in fact, 4 points. I'll take P1 and P2 to be t to the L, 1, 1, and minus t to the L, minus 1, 1, and similarly P3 and P4, plus or minus 1, plus or minus t to the L, 1. So hopefully these points, in fact, lie on the conic. Okay, good. So here's our picture. I'm sort of like, there are a couple ways to draw this picture. I mean, I'm trying to draw a single plane curve, a conic with 4 marked points. But morally, what we're really interested in when writing something like this down over the valued field k is an infinitesimal deformation over the punctured complex plane punctured at t equals 0. So an infinitesimal sort of family around t equals 0. And this equation does happen to define a stable model in the sense that we talked about last time, because you can just see that this is a flat proper family on which the special fiber, when t equals 0, that is to say, is x times y equals 0. And we have specialization of the marked points, 2 on each component. So here is my picture of my stable model, x over r, where the generic fiber is isomorphic to x, and the special fiber over S is a stable curve over the algebraically closed residue field C. And so the tropicalization then has 2 vertices and an edge corresponding to the 2 rational curves meeting at a node. The vertices have weight 0, they're rational after all, and the marked points, which I'll draw as legs on the vertices, showed that the result really is stable. Now, what is the length associated to this edge? I claimed before that it was L, exactly L. And that's because I cooked things up specifically. I mean, this is the easiest example you could possibly encounter. The local equation of the node. Okay, so this node here, I guess, is, I don't know what to say. The local equation is precisely x times y equals t to the L. So let's look at the patch where z is not 0, for instance. So here the local equation is x times y equals t to the L, and t to the L has valuation L. So this is the tropicalization. Okay. So that's the picture of where we've gotten with, as far as abstract tropicalization is concerned. So I'm going to move on to now a sort of purely combinatorial sort of middle portion of this course on tropical curves. Unless there are any questions on this. Yeah?
So here you could say this because you started from an equation which is already the model, right?
That's right, yeah.
Okay.
Okay, so how do you do this in general? It's like not trivial, first of all. Okay, but if you're given some ideal, like some homogeneous ideal defining a projective variety, then the process is called saturation. So algebraically, you're saturating out by t. Does that make sense? So for example, if I gave you some sort of stupid way of writing this, like t xy equals t to the L plus 1 z squared. Okay, so you don't want, this is not a model. Passing to t equals 0 does not give you what you want, but the algebraic operation of saturation just takes out all your extra powers of t. So that can be done on an ideal theoretic level, as you're probably familiar with from algebra. Okay. Yeah, but I mean, I think that in general, calculating these things is not, it's known that it's possible, but algorithmically, it's not at all sort of worked out clearly, I would say. Yeah. Great. Anything else before I move on to combinatorics?
What
Yeah.
is the geometric meaning of this TL, of this valuation L? Increasing L, what does change from the geometric point of view in the deformation?
Yeah, exactly. So if I didn't give you L, then I would be telling you essentially just the combinatorics, just something about the combinatorics of the special fiber. The L tells you something about the way in which the special fiber is being smoothed out in the given family that I've started with. So it is some partial information, basically, about the speed of deformation of this node in the family. That's what I would say roughly. So I mean, specifically speaking, this node actually, well, okay, so maybe I'll leave it at that if that's a reasonable explanation for you. Yeah. Uh-huh.
Something I could say is that it is the nature of the singularity of the total space.
That's exactly right, yes. This is the width, so maybe it's more familiar called the width of the node. In other words, this, so this tells you sort of the A, L, or AL plus 1 or something like that, that you have an A, L, I might get the indexing wrong. So let's just say AL singularity at that node, considered as a point in the total space. Yeah. But I think about it as giving me information. So if I have some tropical curve and the lengths of the edges are like 1 and 2, then I think about sort of relative speeds of the nodes forming, so to speak, in the surface. Yeah, that's the best I've got. But okay, so better to say that it tells you the sort of how bad the singularity of the surface is there. Okay, anything else? Okay, combinatorics then. So here's the goal of the next section of the course. It is to construct a plausible moduli space of genus G n-marked tropical curves. And I'm going to do this more or less from like first principles, combinatorially speaking. And only later will I make the case, and this will be sort of the content of the last 2 lectures. I'll try to make the case that this construction that we're about to go through, just following our noses combinatorially, actually is useful algebrogeometrically. What we're about to construct is a cone over the boundary complex of the Deligne-Mumford compactification by stable curves. But I'm going to do this one step at a time. So let's do the combinatorics now, involved in the construction of the tropical moduli space MGN trop, which at the moment should just be a space that reasonably parametrizes the tropical curves up to isomorphism, the tropical curves of genus G with n-marked points. Okay, this is due to Bernetti, Mello, Viviani. And I would say building on work of Caparasso, also Mikhalkin, Jarkov. And for those who are interested, it somehow has as an ancestor the work of Color and Voigtman in outer space. So there's sort of already been in the literature plausible and very interesting, in fact, spaces of marked metric graphs, basically. But okay, let's just start from first principles. Okay, so I want to construct some topological space which parametrizes isomorphism classes of genus G and marked tropical curves. So let us first prove the following easy fact, which is that there are only finitely many like combinatorial types. In other words, vertex-weighted marked graphs of type Gn. And in fact, this fact will follow from the following calculation, that if, let's see, yeah, let's say this. Every such type, so every such weighted marked graph has at most 3g minus 3 plus n edges, and this is attained. Okay, let me even say more specifically, and this is attained, this bound is attained. By any combinatorial type that's maximal under the operation of weight contraction that we defined last time. So this is attained by any such GMW that's maximal under the combinatorial operation of weight contraction. Okay, I set this as an exercise in my notes. And it is an exercise, but let me work it out. Because the reason we want this is that we want to do the following. We want to just fix a combinatorial type and parameterize all of those tropical curves and then vary the combinatorial types. So it's useful to know that, of course, there are only finitely many. Okay, so let's work out the exercise, which is to prove the second fact. Of course, fact 2 implies fact 1. All right. So proof of 2. Let's work this out together. So what does a maximal... Okay, here's what we're going to do. We're going to fix one of these types that's maximal under weight contraction, and then examine it and count its edges. So suppose GMW is maximal under that operation. So I claim, first of all, that the weights of all the vertices are 0. And here's why. So suppose I have a vertex V of weight positive. Then I can uncontract. Right, so I can uncontract a loop based at V and decrease the weight. So contradiction to the fact that I was maximal, proving the claim. Is it okay? So if I had a positive weight on a vertex, then please build a loop on that vertex and subtract 1 from the weight. All right? Okay, so next we claim that for every vertex, the number of markings plus the number of half edges, in other words, the number of ends of edges incident to V, is exactly 3. So there's a reason I've been drawing the markings as half edges. You can sort of look at a vertex, and if it has 4 things coming out of it, either marked points or edges, then please just split up. So here's a picture. So we'll just split up in some way via the reverse process of weight contraction. We'll split up that vertex into 2 vertices connected by an edge. Okay, so with these 2 claims, we have a complete sort of an understanding of maximal types that allows us to count their edges. So now, right, so I'm trying to prove that the number of edges is exactly 3g minus 3 plus n. That, of course, is good news in terms of constructing a moduli space. It certainly makes us optimistic in any case. Okay, so now, what do we have? We're going to do the sort of primordial graph theorist's counting trick, which is to double count vertex edge incidences in this generalized sense. So this is like a very useful trick. I'm going to double count the pairs. Okay, what am I double counting? I'm counting V comma H, where H is either a half edge at V or a marked point at V. So by counting these things 2 ways, we'll of course produce an identity, and that identity will prove our claim. Namely, on the one hand, this count is 3V from the second claim. And on the other hand, what is this? So let's count the number of half edges. That's 2E. So 3 times the number of vertices. On the one hand is twice the number of edges. That's the number of half edges. Plus the number of marked points. Does that look right? Okay, good. And from this we deduce the desired equality. So I claim that then the number of edges is 3 times this quantity that stands in for the genus, e minus b plus 1 minus 3 plus n. And recall that this really is the genus of the graph, 3g minus 3 plus n. And that equality follows from the fact that all the weights are 0 on the vertices. So when I say the genus of a graph, usually I mean the graph theoretic genus, e minus b plus 1, plus all the weights. And here all the weights are 0. Okay. So that's proof of fact 2, which was quite elementary. I ran the whole proof combinatorially, by the way, but the fact is I could have run it more algebrogeometrically. I could have counted for you the curves in a maximal Pantz decomposition of a genus G Riemann surface. And we would have done the same double counting and obtained the same result, that on a genus G, like compact oriented surface, connected, you have at most 3g minus 3 plus n simple closed curves with n punctures on the surface. Okay, is that combinatorial calculation fine? Any questions? Okay, so this allows us then to make a plausible tropical moduli space as follows. There are only finitely many combinatorial types of type G, comma n. So let us fix one such. So of type Gn, meaning genus G and marked points. And let us ask, what is a natural way to parameterize the tropical curves of that combinatorial type? Okay, so let me let C of GMW denote, okay, let's see. Let me, for the moment, let C denote the closed real orthant R to the E of G greater than or equal to 0. And the idea is as follows. Sorry, just forget about that for a moment. Let's just think about it. So one way to parameterize all such curves would be to take all possible assignments of real numbers to the edges. So all possible length functions, L from E of G to the positive real numbers. Now that is almost right, except that we're overcounting by potential automorphisms of this combinatorial type. Right, so if you give me, I fix a combinatorial type, and if you give me 3 and 4 versus 4 and 3, you're really specifying the same tropical curve up to isomorphism. So what we would like to do, therefore, is to consider the open cone consisting of all possible length functions from the edges to positive real numbers, modded out by the action of the automorphism group of the combinatorial type. So this automorphism group induces some permutation of the edges, and the permutation of the edges induces the corresponding permutation of the points in this open cone. Okay, so I propose to do the following, which is that with some foresight, we will close up that cone, allowing 0 length edges, with the understanding that an edge marked 0 will be identified with the weight contraction. So if you have an edge marked 0, then contract everything away and you obtain some other combinatorial type. And this is how we are going to glue those closed cones together to make an actual moduli space in the sense that its points are in bijection with isomorphism classes of curves. So that's my definition. Sorry, so that all motivates this definition of some cell C of GMW. And again, to glue all that stuff together, we will define, right, so we'll define an equivalence relation along which we're about to glue. So this is an equivalence relation on all of the cones C. in which one point, let's see, yeah, so let me write this way. So a point x in C of GMW is identified with another one in a different cone. Okay, actually, let me take the equivalence relation generated by these. Yeah?
This joint union is over all the graph of type Gn.
Ah, yes, thank you. So this is over so isomorphism classes of combinatorial types. Yeah, so isomorphism classes of combinatorial types of type Gn. Thank you. Yeah, thanks. Are there any other clarifications or questions? Okay, so we take the equivalence relation generated by identifying 2 points when x is obtained, say, from x prime by contracting, weight contracting, all zero-length edges. Is it okay? So let's, yeah, why don't I even just look at that cone there? So corresponding to this type, the figure 8 of type 2, 0, we have a cone, a closed cone, parameterizing the 2 ways to assign lengths to this, the edges, modulo a z mod 2z symmetry. And we close up the cone with the understanding that if I am to associate a zero-length edge, sorry, 0 to an edge, then we identify this guy with the thing obtained by contracting that edge away in the sense of weight contraction defined earlier. So this will identify ultimately a ray with the sort of boundary, the ray of the 2-dimensional cone I drew there.
Don't you want to contract the zero-length edges of x as well? I mean, both contractions are the same.
Yes, so that's why I carefully wrote this is an equivalence related generated by these. Yeah, thanks. And that's it. Okay, so that's our moduli space. So now we may define. This is our sort of first definition. It's, for me, the most transparent way to at least say what the space is. So it's this disjoint union of these cones modulo automorphisms. Again, this is over GMW of type Gn, and I'll implicitly choose just one from each isomorphism class, if that's okay. And this is modulo that equivalence relation that allows us to glue the cones together basically along the faces. And by construction, I hope it's clear that at least it's the case that the points are in bijection with tropical curves. Is that clear? Wait, was that a no? I feel like... Okay, so let's think about this, the decomposition of that space according to the interiors of the cones, right? So there's a stratification of this space by the interiors of the corresponding cones in which the length functions were never allowed to go to 0. And because we mod it out by automorphism, the interiors of these cones precisely parameterize actual tropical curves of that fixed combinatorial type. The equivalence relation is just the thing that allows us to glue these together in a reasonable way, taking into account the relation of weight contraction. Are you more convinced? Okay, good. So then if you don't mind, let me give you a slightly better quote-unquote definition that's a bit more categorical. And it will be useful when we try to interpret this space, not just as some combinatorial space we cooked up, but an actual boundary complex of the Deligne-Mumford compactification. But I think for intuitive purposes, this is a good description. Oh, let me just draw a picture so that you can't complain. Okay, so let's do M12 trop. And for this picture, I'll recall for you the PO set, the partially ordered set of 5 combinatorial types of genus 1 with 2 marked points. And again, I'll draw my marked points as little legs coming off vertices. And again, I'll just use the convention that if a vertex has weight 0, I'm not going to write it. There are too many zeros. Okay, so here it is. So this is a vertex now of weight 1. It was obtained from this one, for example, by contracting the loop. Here we are. Okay, and there's a poset structure according to weight contraction, which I'll draw in this diagram. Okay, so let me try to draw a cartoon of the tropical moduli space. So I have two-dimensional cones upstairs, one with a Z mod 2Z symmetry on it. So this left cone corresponds to the combinatorial type on the left. And this right two-dimensional cone, this is filled in, corresponds to the top right combinatorial type. And let's notice one sort of subtle but somewhat important distinction. Both of these types have Z mod 2Z symmetries. In the right-hand side, it's the symmetry that flips the loop. But the induced symmetry, the induced permutation of the edges is trivial in one case and non-trivial in the other. Okay, so I'm trying to illustrate the cone R2 modulo flip in this way. And that's just a sort of cartoon illustration. I mean, really, I'm taking, this is just a topological space, so I should probably just draw half a cone for you. But let me draw the extra structure in this way. And secretly, the reason is that there's a way to define these objects that's a bit more abstract and will take into account these symmetries. Okay, anyways, I'm still drawing this space. So now we have one-dimensional rays corresponding to the types in the middle row. And finally, I have a vertex, right? There's a zero-dimensional moduli associated to that combinatorial type. Sorry, this should be a weight 1. I'm sorry about that. Okay, so that is my attempt to draw a tropical M12. Is it okay? All right. Are there any questions?
So how about those infinite length edges that you talked about in the beginning? I mean, they're not part of these, right?
That's correct. Right now I'm drawing M12 without the bar.
Oh.
Yeah. So if I wanted to extend the space, it's, I guess it's not hard to see what to do, is it? So you put in some boundary of the cones, right? You compactify the cones themselves, starting with, over here, you take R greater than or equal to 0, union infinity, and then you just proceed. Yeah.
So on the
Yeah.
right cell, you're saying so there's an automorphism that actually joining the cone.
Exactly. It's a flip of this loop. It's an honest automorphism of the graph, but it induces the trivial permutation on the edges of the graph. Exactly. So this permutation, this action here is a permutation. Sorry, it's induced by permuting the rays of this orthon. Yes, thank you. Yeah. Was that a question?
Yeah, so the two edges that are labeled with the same guy that's contracted in the two different two-dimensional cones.
This guy.
Yeah.
Yeah.
Should we think of those as being identified then?
Yeah. You know, maybe a better picture for me to have drawn would be to draw it like this. Right, because after all, I'm working in the category of topological spaces, at least for this exposition. So this is maybe a better picture. That ray only comes up once, so to speak. Yeah. But you can take a more abstract view of this kind of space. At the moment, I've constructed as a topological space. In just a second, I'll propose to construct it just a little more abstractly as obviously living in the category of generalized cone complexes. And you'll see what that is. And you can make an even more abstract definition in which this is just the geometric realization of like some pre-sheaf on some category. And for that, I'll send you to the references in my notes. Yeah.
The dotted? Yeah, is that?
Yeah. This corresponds to the locus of tropical curves of this type, where the two edges have exactly the same length. It's the middle. It's the middle of this cone. Yeah. Yeah, thanks for asking. Okay, anything else? Okay, so let me just then tell you, if it's okay, I'll tell you the same story with a slightly different perspective. So, it's a little more natural to construct this as a co-limit of a bunch of cones over an indexing category of stable marked graphs. So, well, I was going to write better, but let me not. So another way. So, and I'll just say this somewhat briefly. There is a category of stable n-marked graphs of genus G. So the objects are, well, so this is the category whose objects are these guys. And the morphisms are, I'll say it somewhat informally. They are compositions, all possible compositions of weight contractions and isomorphisms. Isomorphisms in the category of graphs, which you can perhaps guess what they are. So a morphism is something that looks like a weight contraction, possibly a trivial one. And given, so this category is about to be an indexing category over which we take a co-limit of cones. So let me let sigma of a combinatorial type, GMW, be just the actual orthant r greater than or equal to 0 to the, and you have E of G copies of that. So this is just like an orthant. And now notice that for every morphism in my category, so this is a morphism of JGN, there is induced, so this is sort of obvious, there's an induced inclusion of edges of the smaller guy to the bigger guy, right? So if you look at a graph and then you do a weight contraction, you can identify the edges of the smaller type with a subset of the edges of the bigger type. That's all I'm saying. And this inclusion induces, of course, an inclusion, possibly non-proper, of a face inclusion. So this is a face inclusion, possibly non-proper, of one orthant into the other. So let me use my notation. Sorry. So this is sigma of G prime M prime W prime identified or included now with into sigma of GMW. Sorry. And now we define, let's redefine tropical MGN to be the co-limit of the sigma of GMWs over this category. So this is the colimit over the indexing category of stable marked graphs, and this is just a slightly more, I guess, natural way to talk about this construction that we just did. It's the same construction. So maybe to convince you of that, I'll draw another cartoon in the same case. Genus 1, 2 marked points. So e.g. M1, 2 trop, I can think of as obtained by taking a bunch of these orthents. I'll draw the orthents sort of positioned so that it's hopefully clear what they correspond to in my poset over there. So I have a two-dimensional cone, 2 rays, and a point. And then I glue these. According to the identifications I just made. So basically, for each way to identify one type up to isomorphism with another type, the weight contraction of another type, you get an arrow. Something like this. And crucially, there is included in this category the automorphisms of automorphisms? Yeah, isomorphisms in the category. In other words, automorphisms of combinatorial types. So these face inclusions need not be proper. They can be self-gluings of cones. And excuse me, when you glue up that diagram, you get the picture on the right-hand side. Is it okay? All right. So next time, we're going to be building towards seeing this space not as purely combinatorial, but as naturally associated to the Deligne-Mumford compactification. But for today, maybe what I'll do, at least for a few minutes, is to give a few more examples. Okay, and these are like good examples to know. They might not be so algebrogeometrically motivated, but the point is that these spaces do and have come up previously in the literature, at least in some cases. So the first example is M0n. So this, if you think about it, what do curves in M0n tropical look like? Well, they have genus 0 with n marked points. That means that all the vertices have weight 0 and all the graphs, the underlying graphs, are just trees. So this is a tree space. It's a space of trees with internal edges with some lengths, alpha and beta, say. So this is a sample point of M05 trop. And in general, these spaces preceded tropical geometry. These are known as the space of phylogenetic trees. On n, there's a slight convention change, but let me just say for the moment n taxa. And this is a space already constructed by Billera, Holmes, and Voigtman. Okay, I'm just telling you this stuff like for culture. I know it's not algebrogeometrically motivated quite so much, but this is good to know. So basically, there is some space that, in principle, phylogeneticists are interested in because it parameterizes the ways to equip trees with n-marked leaves with length in the middle edges, with the idea that if these markings represent, like, say, genetic sequences of present-day species, and you want to figure out, you have sort of data about how different they are, and you want to hypothesize what some evolutionary tree structure is above them. Then the space in which you're working, the space where you want to make approximations, is this space, tropical M0n, genus 0 n-marked curves. Okay, so this is a well-known example, and here there's no quote-unquote stacky structure. There's no automorphisms of combinatorial types like this, because the marked points must be fixed under any automorphism. Okay. For G0, for small g, you can see, okay, I'm not sure what to say here. You can see my website for pictures of the posets associated to these. So an example, let me even just say this example. M50 is a space of dimension 3 times 5 minus 3. I guess that's 12. And this is a space, so it's a generalized cone complex, as all of these spaces are, which basically just means that they live in, they are of this form. They are obtained by gluing cones along faces. And it has 4,555 cells. So if you want to look at those cells, you can download them from my website. And in general, there's software you can use to compute these things. So I can talk to anyone who's interested about computational aspects. All right.
So you mean cells of maximal dimension?
Total number of cells. So like here I would say there's 5 cells. There's 4,555. And you can download like a big PDF poset that is the analog of this poset here. Okay. Finally, let me tell you some facts about M11. I don't think I'm going to explain them in great detail, but I'll just tell you the situation. So this moduli space of tropical elliptic curves, abstractly. Okay, what is this space? We should be able to figure this out together. There are 2 combinatorial types, right? There's always the unique minimal combinatorial type, which of course corresponds in MGN bar to the open locus MGN inside MGN bar. It consists of a vertex of weight g, in this case 1, and a single marked point. And there's one other combinatorial type which arises when you unfold that weight into an actual loop. So here's my poset, and here is my tropical moduli space of elliptic curves. It's a ray. Is it okay? Okay, so it's worth remarking that let's put together the various threads of this course so far. Having constructed now tropical moduli space, I can at least define a map of sets as follows. And I'll define the map of sets, and then I'll maybe just circle back quickly to M11 to tell you what that map of sets is in this case. So note, we have defined now altogether, let me just say for a fixed field, a valued field, K, complete and algebraically closed, etc. But that's not too important. A map of sets, MGNK to MGN trop. That was the whole point, right? So we spent a lot of time defining the tropicalization, the abstract tropicalization of a curve with n marked points of genus G, smooth over field K to the tropical moduli space, which I'll just write trop xpi for the moment. And as I briefly remarked, though it's not, I think, ultimately going to be central to this course, this can be extended to a map from the compactification by stable curves to M bar GN trop, whose construction I alluded to before. It's obtained when you allow infinite lengths on the edges. And this map is sort of, I would say, an interesting map at the core of a lot of what, a lot of work in tropical geometry. And I'll remark without writing it that these maps can be put together into a big old map from a Berkovich analytification of the moduli space. But at the moment, you can just think of it as a map of sets. And we've studied before this map pointwise, and now we're putting it together into a map of moduli spaces. Okay, so what does the map look like? Oh, yeah.
About this map, something I'm not getting.
Yeah.
I mean, you are sending a curve to a stable model, or to, because these are smooth curves.
That's
so
right.
The dual graph is pretty easy.
I agree. I agree.
So this map is this one I'm talking about, or is not?
It is not, because that would be a boring map, sending everything to the unique cone point of moduli space, tropical moduli space. So I'm talking about the tropicalization procedure I reviewed in the first 10 minutes, where when you take a smooth curve, exactly as you said, you have a stable model of that curve. That stable model has a special fiber, and you have a metrized dual graph of the special fiber. That's the tropicalization. Okay, I said it in a somewhat clunky way. It's actually a fact that the tropicalization is intrinsically associated to the curve x, and it's that tropicalization I'm talking about. Is it okay?
In fact,
Yeah.
I think my problem is that I don't see this so intrinsic, but I got what's the problem. Okay.
Okay, yeah. I am, I guess, stating, but I haven't justified that the tropicalization map is an intrinsic way to associate some like metric graph plus some stuff to a curve over a valued field. Yeah. Mm-hmm. And I think in the comment from Christian yesterday, the way to justify it is to say that it's intrinsically associated to the analytification. Yeah. Okay, and actually, so maybe to help with your question, let me explain to you what this map is in the case of elliptic curves, without justification. So, e.g., when g and n are both 1, we're in the case of elliptic curves. There's a sort of beautiful, like very simple description of this tropicalization map. So M11 K, tropicalization on the level of moduli spaces, M11 trop. Is as follows. So I have to tell you, you give me some elliptic curve over a valued field, and I have to tell you either that its tropicalization is this tropical curve right there, consisting of a single vertex, or I have to tell you that it's got a loop, and I have to tell you some length of the loop associated to it. And the story, though I don't have time to justify it, is that if the valuation of J is non-negative, J is the J invariant, so let E over K be an elliptic curve, and J sub E, say, is the J invariant of E. Okay, so what the J invariant is some number over K, some number in K, that precisely identifies your elliptic curve up to isomorphism. So it is a parameter for the, say, coarse moduli space of elliptic curves. Now, it turns out that if the valuation is non-negative, then you're in the quote-unquote good reduction case. In other words, in the language of tropical geometry, this amounts to the fact that the tropicalization in the abstract sense of E is the single vertex tropical curve. And if the valuation of J is negative, then the tropicalization of E is the loop with one marked point. And what is the length of the loop? It is the negative of the valuation of the J invariant. These are J sub E. Okay, that's, I think, a beautiful story, and there's a lot more that one could say. The basic reason is that when the valuation of the J invariant is negative, then there's a sort of, what's it called? A uniformization, a non-Archimedean uniformization of the form. Sorry, maybe I'll just say quickly. So when J sub E has negative valuation, your elliptic curve is in some sense isomorphic to the multiplicative group modulo a multiplicative sublattice, a discrete sublattice. And here Q is called the Tate parameter of E, which happens to have the property that the valuation of Q is minus the valuation of the J invariant. Okay, so this is like the Tate uniformization of a non-Archimedean elliptic curve, which should remind you, at least morally, at least after applying an exponential function to change addition to multiplication, it should remind you of the usual uniformization of elliptic curves. Now, with this story in the background, it's maybe a little more plausible that there's a loop here of length valuation of the Q, the Tate parameter, and the length of the loop is more or less obtained by taking a sort of infinite cover and then identifying every point, identifying 2 points when they differ by the length valuation of Q. All right, and there's a lot more to be said here, but at least I can tell you very specifically in this one case exactly what my map of moduli spaces over there looks like. Is it okay? Okay, so thank you.